We have is complex video reasoning and robustness evaluation suite for video large multimodal models. This is one of the most interesting challenge we had. We had the maximum number of submissions, unique submissions, and most of the teams competing for this challenge. So the overview of the challenge is as follows. This benchmark was specifically curated for understanding and evaluating like complex reasoning, fine-grained reasonings, and the model robustness to basically understand what's some hidden dimensions in the videos and ask some non-simple questions or complex questions which cannot be directly answered just by looking at the video. So for that, we had like this 11 real-world video dimensions, for example, fine-grained action understandings and partial clips and multiple actions in a single videos. And we also, and so this benchmark basically also reveals the existing VLM's weakness and the areas of improvements where they can be improved. So this challenge was aimed to for the teams to highlight those existing weakness and come up with the strengths and the problems and some solution to overcome those challenges. So in this data set, we had two splits. One of them was the validation split. We had this 2,400 question answer pairs. All of them were open-ended, and they were from 214 videos. For the test set, we had an independent set of 555 open-ended question answer pairs that arise from 57 videos. For the validation datasets, we compose our dataset construction from some of the existing famous benchmarks. For example, something we do, Cater, Shiraz, ActivityNet, HMD, Human Motion Detection, and then YFCC. And nearly 40% of the dataset was composed from internet scraping, YouTube videos, and open license videos. For the test set, this entire data set was collected from scratch and manually curated from YouTube across the 11 dimensions. So we have like a pretty independent and balanced subset when it comes to the test set. And the entire data set went through the human verification and rechecking and filtering to make sure that we have the highest quality of open-ended question answer pairs. And then we followed the similar pipeline of this CVRR to make sure that there's no out-of-domain distribution for this particular challenge. Some of the examples for a challenge from different domain, for example, this fine-grained action understanding and then interpretation of social context and partial actions. So evaluation framework, we hosted our evaluation framework on the Grok, and then we use LLM as a judge as an evaluation framework. For that, we use Llama 3.370B Instruct, which is a pretty recent model. It's an open source model, and it has a great support in the Grok. So we had a pretty good judgment there and pretty fast evaluation as well. Each evaluation took like nearly 5 minutes on the Grok. So this is the baseline results that we wanted teams to beat. This is from one of the papers. If you want more information, you could take a look at the paper as well. In terms of submission statistics, we had like total 96 successful submissions, and then more than 60%, 69% of the teams, like these submissions were test submissions, like almost 29 to 30 submissions for the validation submissions. We had the most unique teams in this, which is number 12. In terms of winner, we have three teams. The team that came first was Team Dive, which have the accuracy of 80.18%. This is Panasonic team. For the second position, we have a tie between this Angis KMG and Opus Club. They both achieved nearly 78%, which is pretty competitive. For presenting these certificates, we would like to invite Dr. Sheen on the stage. He is a senior AI ML engineer at Apple. Can we please have you on stage? Team Dai for the winning presentation.
Sorry, we cannot go there.
Yes.
Winning presentation.
No, we have someone on the behalf of them.
No, sorry, no.
Yeah.
No, we have.
Yeah, well, so right now we are awarding the certificates to the top two teams. We'll get back to you once the presentation for the winner, okay?
Okay.
Yeah, just.
Dr. Sheen, we'd like you to stay for one more minute. Thank you. So for the second team, we have this Angis KMG. Do we have any someone on their behalf, on the representative to collect that? If not, Rohit, can you please collect on their behalf and give it out to them later on?
A lot of money. Someone should come get it, right?
Yeah, they said, okay, I think.
No check for them?
No
Just
check
the
for that,
first one.
sorry. Thank you.
One more.
No more? Okay.
Yes, we have the tie for the second position. So for the third, we have like Opus Club. If you have someone
Yeah.
on the behalf of them or themselves, even better. Like, all right, thank you so much, Dr. Singh. You may begin. And now can we please request Team Dive to share the screen for the presentations?
Okay. Can see?
Yeah, we can see. Go ahead.
Okay. Good afternoon, everyone. My name is Mihail Kamoto from Panasonic Connect. Thank you to the video LLM's organizers for this opportunity and their organization of this competition. Today, I will present our work, deep search, iterative video exploration, which won the CVRR challenge. First, let me briefly introduce our team. We are Team Dive from Panasonic Connect, a B2B solution company within Panasonic Holdings. Our team members, Mihiro Kamoto, Tatsuya Ishibashi, and Nori Kuo, are AI researchers specializing in vision language modeling and video QA. And the CVRR challenge evaluates video LLMs on complex reasoning and robustness in real-world scenarios, aiming to raise the performance gap between AI models and humans. And to tackle these challenges, we developed the Dive Deep Search Iterative Video Exploration. Our core concepts are inspired by two key ideas. First, the human problem-solving process, breaking down complex questions into simple sub-questions and understand the intent. Second, from OpenAI deep research, multi-step inferencing and iterative reasoning for deeper understanding. While deep research search is on the web, our approach extracts information from video content. Dive's framework is a six-step iterative processes. Intent estimation, understanding the question intent, and the question breakdown, decomposing complex questions into simple sub-questions, and question answering, and QA agent equipped with specialized tool, and QA question refinement, updating subsequent sub-questions based on the previous answers, and continue judgment, deciding whether to continue loop and final answer generation. We also create object-centric video summaries and input them together with the video and question. We release the code on GitHub soon. And here's our key strategy, question breakdown. For instance, to the question, is the boy using a hairdryer on the girl hair? A baseline model might answer yes, this is incorrect. Our method breaks it down and starts from is there a boy and girl present, and proceed step by step through simplified sub-questions. And our QA agent uses GPT 4.1 and Gemini 2.5 Pro with complementary strengths. And then it judges whether sufficient information has been gathered to conclude. Dive improves accuracy by dynamically deciding whether more analysis is needed. Through this iterative process, Dive correctly concludes that he's not drying her hair with a dryer. This is important for achieving high accuracy in complex scenarios. Another critical aspect of Dive is intent estimation and video summarization, which work together for better reasoning. For intent estimation, our system understands the hidden intent intent beyond literal words from the question and video summary. For example, for this question, how many cards were the intent is counting forward moving cards visible ahead of camera light before tunnel entry. For video summarization, we combine multimodal LLMs and object detection. LLMs provide excellent understanding, but they have high cost and have limited context window. Therefore, we cannot process all frames with LLMs alone. And object detection excels at spatial temporal tracking, and all frames can be processed, but lacks semantics understanding. Our approach generates fine-grained video summary using specially sampled frame and grounding dyno for object detection and GPT 4.1. This feeds into our reasoning pipeline for detailed analysis. So how did DIVE perform? DIVE achieved state-of-the-art result on CVRR ES benchmark and validation data 91% accuracy overperforming other teams and the GPT-4 baseline, and test data 80% accuracy are also leading the board. These results demonstrate DIVE's effectiveness. That concludes my presentation on DIVE. Thank you very much for your attention and welcome any questions or comment. Thank you.
Any questions for the team?